Okay, so add these to your notes, please. This is further evidence, and this specifically is evidence that IB likes to ask about for the presence of this resonance structure we call benzene. And so further experimental evidence for resonance energy. This goes right along with our evidence of benzene is relatively inert because of all those delocalized electrons in the pi cloud. Benzene is has not got alternating single and double bonds, instead has a hybridized bond that is shorter than a single bond but longer than a double bond, so it's a hybridized bond orbital type thing. So this is more example here. And so if we look at the hydrogenation of ethene, the carbon to carbon double bond, that adding a hydrogen to it is an exothermic reaction, and it produces about 26 to 30 kilocalories per mole that we hydrogenate. If we compare that to, let's go ahead and break a double bond within a cyclohexene molecule. And so we break that double bond, we get about 28.6 kilocalories. And we would expect then, if we have to break two double bonds, that we would have double of that. And that's pretty much roughly exactly what the change from exothermic 28.6 kilocalories is as compared to 55.4 kilocalories. And so as we can see, we could make the theory that, well, our estimated energy release of the full hydrogenation of benzene would be 3 times 28.6, or we would expect it to be somewhere around 86 kilocalories. But when we actually experimentally fully hydrogenate benzene, in other words, turning it into that cyclohexane, like we did from cyclohexene and from 1,3-cyclohexadiene, turning it into the cyclohexane doesn't actually produce 86 kilocalories per mole. In fact, it only produces 50 kilocalories per mole. And so we have to ask ourselves, what is actually going on? We expected a much higher amount of exothermic reaction being given off. The answer is somewhat interesting, and it's the evidence for our presence of the resonance structure. So since there is a difference of 36 kilocalories per mole, that means benzene is actually 36 kilocalories more stable than what would be expected for just a plain old cyclohexane, which is what we're creating, or a cyclohexene that we have going on there. So then what we have to do is we have to be able to say, well, what is this? And we say that is the resonance energy for benzene. And as long as it is more stable, as in it's producing more kilocalories, or it's producing less kilocalories than we expected, then we say it's more stable. So this is meaning that benzene is going to react in such a way as to preserve the aromatic structure and retain the resonance energy. In other words, it's always going to try to react in a way that it retains its resonating structure and resonance energy. Let me get rid of that. All right, so our properties of arenes are, once again, that it comes from coal, that's pretty much colorless, it has a strong smell, it's insoluble, it's less dense, it's very nonpolar, it only has LDF forces as part of its IMFs, it is basically inert, it really hates to react unless we force it to, as you're going to see next time, and it has no single and double bond alternating. Instead, it has a resonance hybrid structure. Okay, everybody, thank you very much. Make sure you've taken all your notes. I'll see you on Monday. Bye-bye.